Good morning, good afternoon, wherever you are in this world. And welcome to this webinar. Frank and myself happy to be here to talk to you about quantum threats. All right, well then let's get started and introduce ourselves. So I'm Isabelle Marie. I'm a field CTO. I'm based in Europe, helping some of our key customers with our platform. And today I'm joined by Frank Lehman, Dr. Frank Lehman. I'll let you introduce yourself, Frank.
Yeah, my name is Frank. I'm based in Germany. I'm a WSO2 technical fellow in charge of running the technical strategy with my colleagues at WSO2. And I also have a second hat on. I'm a professor at the University of Stuttgart, and I'm running a couple of quantum computing projects since many years with industry partners. And of course, quantum threats are extremely important in this context.
Absolutely. And my colleague here is very humble as one of the sommities of the world in quantum computing. Any question you may have, I'm sure he can answer. So let's get started. Why are we here, right? Why are we doing this webinar? What are we talking about? And the idea is that Q-Day is getting closer. What is Q-Day? You know, we've heard maybe of D-Day. We've heard of the year 2000 day. There is this like clock ticking that something really bad is going to happen at some point in the future. This point in the future is what is going to happen when quantum computers, which do exist today and their companies are actually using them today, are going to become like more mainstream. And what is the threat that the power of those machines is going to bring to us? And really the key of the crux here is why are we doing this? Why should I worry about this now? Because I think the call to action really of this webinar is that while maybe quantum computers seem to be something which is, far away, that Q-Day is kind of far away, it is something really want you as a call to action to start worrying about today. And so when is Q-Day, by the way? So very, even recently, Q-Day, maybe, when we were talking with Frank, maybe a month, 2 or 3 months ago about this, it was like, oh yeah, maybe, 2035, 2040, maybe further than that. We're not really sure because there were some calculus that had been done that were showing this is kind of far away, maybe more in the future. But very recently, we're talking beginning of June, there was this new research that was published by some researchers at Google that have been working on this topic before, saying that they have developed, a new methodology that brings that Q-Day much closer to us, much likely, they've reduced the complexity and the necessity of the power that, Frank is going to talk about this a bit later, but at the high level, whatever we thought would take a lot of power to do, thanks to new, breakthrough advances, is going to take much less power to actually do it. And what are we talking about here is being able to break basically any of the encryption algorithm that we're all using today, right? Including RSA or SSS, etc. And why do we want you to worry about this now? Is, if you look at this picture, is let's say you start worrying about this like right after this webinar, like we've convinced you, like right after this webinar, you start worrying about this. But you already have some data that has been encrypted with RSA, ECC, whichever algorithm. You have that stored somewhere because depending on your industry, you have the requirement to retain that data for a long period of time, right? It could be commercial data, it could be tax, it could be financial. Depends on your industry, whoever is on this call. So the equation here is if this data is already saved and written and encrypted with a non-quantum safe algorithm, and let's say that Q-Day is like 2 years from now, which is before the end of your retention time, then the risk here is that this data, that's it. It's doomed. It can be decrypted, and there's nothing you can do about it because it's already encrypted. It's already stored, and there's nothing you can do. So why we wanted you to start early is that you start early encrypting with quantum safe algorithm, all the data you save from now, right? And that's really the call to action that we want to make, right? At the high level. Do you want to add something to that, Frank, on top of what I said?
Oh, I'm absolutely fine.
Okay, well, but now, Frank, that's the part where I have to stop and you have to start and you have to start because you're
Thank you.
what is this all about? So what is, tell us about quantum computing 101 as if we're 10 years or maybe 20, like your students.
Okay. So what we see here on the left side is what we all know what a bit is, right? The bit is either in state 0, the red arrow, or in state 1, blue arrow, true or false. And the quantum bit is completely different. It can be true and false at the very same time. And there is on the right side a sphere, it's a unit sphere, it's a surface of a ball, and the qubit can have any value on this surface. So a qubit can have an infinite number of potential values while you manipulate it in a quantum computer. And you're not manipulating only a single qubit, but next slide, please. You manipulate a whole register. You can bundle qubits like you can bundle bits in a classic computer into a register. You can bundle qubits in a register. And then you see the north pole, you have the false values, and the south pole, you have the true values, and each individual qubit can be any point on this ball. But if you now consider that you have n qubits, right, you have 2 to the power of n different combination of zeros and ones. And you have them at the very same time, and you can manipulate them at the very same time. So I'm cheating a little bit because I don't want to explain what entanglement is. So if you have specialists here, so you have 2 to the power of n qubits. And if you want to simulate that on the classical computer, you would need 2 to the power of n bits to simulate the states that are in the quantum field at the same time. That means 2 to the power of 300 bits you need. That means you need to turn each and every atom in the universe, in the whole universe, into a bit, and in order to simulate only the content that you can store in a quantum computer. And we call this quantum parallelism, right? You can manipulate a huge amount of data in a single step, right? Imagine every atom is a bit. You can't do it. In practice, you can simulate 44 to 45 qubits, right? You need thousands of GPUs to have 64. And in order to get 1 qubit, one need to double the number of GPUs. So it's impossible to simulate even 50 qubits. Next slide, please. And this enormous power of a quantum computer, this quantum parallelism and so on, allows you to build very new algorithms. For example, to crack, as Elizabeth told us before, most of the current security algorithms that are used to practice today, for example, RSA. If you're familiar with RSA is based on the fact that you have a key, and this key is the product of 2 large prime numbers. And if you analyze that with a bit of mathematics, and I'm not going to do that, Isabel said don't do that, but if you analyze it, how to crack prime numbers, you need to determine the period of a function. So period basically means you have a trigonometric, like the sine curve, but it's periodic. And what we can write down in mathematics is cracking or breaking a number into prime numbers means you determine periods. And even more mathematically, this period finding is called computing a discrete logarithm. So it sounds terrible. But most of the current algorithms we use for encryption is based that the problem of computing discrete logarithm is incredibly hard. And then there came a very famous quantum algorithm by a colleague, Peter Shaw, who invented the Shaw algorithm. And this Shaw algorithm can compute discrete logarithm. That means it can crack RSA, it can crack elliptic curve, it can crack Diffie-Hellman, and so on. All the stuff that we use in practice today. But it comes at a price because we need a quantum computer with a lot of qubits and a lot of stabilities. And this quantum computer is not yet out today. This is what Isabel elucidated before. She said, well, we need to wait until such a powerful quantum computer is there. And this powerful quantum computer is referred in the literature as crypto-relevant quantum computer, as you see in the box on the right thing. And if we have such kind of a powerful quantum computer, you can crack RSA 2048 in an hour or a few hours. And this is shocking because RSA 2048 has been invented because traditional supercomputers will need the lifetime of the universe to crack such a key. And now, if you have the CRQC, you can do it in an hour. And this new hack that Google did, this new modification of this algorithm, needs 1 million qubits, and so less qubits than expected before, but it takes a week to crack this RSA 24. But more shockingly, ECC is much more modern than RSA. It has been created because it is as complicated as RSA, but needed smaller key sizes. But ECC, as it turns out, can be computed cracked much faster than RSA in minutes. So any crypto algorithm that is based on elliptic curve can be cracked much easier. It's a severe threat because these computers are evolving. But some vendors announced a million qubit quantum computer for end of this decade or early next decade. So the time is really coming, and there is a real threat that Isabel and I want to point out. Isabel, up to you.
Absolutely.
Sorry.
Yes, absolutely.
Absolutely. So what is the rescue? The rescue at hand is, it has to do with lattices. What the hell is a lattice? You see here on the left side, you see a figure with green dots. The green dots form the lattice. The lattice in this plane, for example. And the lattice is spanned by 2 vectors, the blue vectors. The blue vectors, if you multiply them and you add them, you get these green dots in the plane. But a lattice has multiple of these so-called bases. You also have the red vectors. The red vectors, one down, one here, they are very strange. They have different length. The angle is big between them. And it turns out that computations in a lattice based on the blue arrows is much easier than on the red arrows. And the new crypto algorithms, they use that in order to come up with problems that are not being cracked today by either quantum computer or classical computer. Let's turn to the right side. On the right side, what is happening is, if you use the blue basis, you can transform a message that you want to encrypt into a spot on the lattice. See the blue dot here, which is the message M. And then you disturb the blue bullet a little bit and result in M star, which is the red dot. The red dot is now the encrypted message, because in order to decrypt it, you need to compute the blue bullet again. But the blue bullet is hard to compute if you only have the red arrows on the right side, right? And this is learning with errors. You want to learn the undisturbed blue message from the erroneous message, M star, the red message. And learning with errors is a deep mathematical problem where it's an exponential problem. It's even worse than RSA, significantly worse. No problem, no solution is basically known. And this lattice-based cryptography has been standardized by the National Institute of Standards in the US, called ML-Chem and ML-DSA. ML means module lattice key encryption, key encapsulation mechanism, and ML digital signature architecture algorithm. And they are based on well-known algorithms called Kyber and Dilithium that some of you may have heard before. So it's a completely new kind of mathematics that has been invented that cannot be cracked today.
All right. Now, this is all great, Frank. Now, I think, unfortunately, we're not all ready to just switch from one day to another to all RSA, ECC, everything we know so well, to post-quantum algorithm. And, this has been clear. Plus, we need to build trust in those new things. Like, we trust RSA, we trust ECC. We've been using them for so many years. So what are we going to do? We're going to take a dual approach, right? We're going to try to use those two together. Is that what we want to do, right?
Mm-hmm. Yes. So what is done today is, what is the suggestion that you should do is, if you don't trust the quantum algorithms, you, on the left side, you encrypt your data both with a classical algorithm and a post-quantum algorithm. So, for example, the orange data is first encrypted classically, and in addition, the encrypted data is encrypted via quantum algorithm. Or on the left side, on the right side, you have signatures. You can associate your message with a classical signature as well as a post-quantum signature, right? If you trust the classical algorithm, you are fine. And then you can get experience. How does the post-quantum algorithm behave? Are they slower and so on? And Isabel will elucidate that a little bit later. And then when you trust the quantum algorithm from that time on, you are only using the post-quantum algorithm. And this is called the hybrid approach. Hybrid because you use both classical as well as quantum. And what we have done also is we extended TLS, right? So TLS, what you see here, the figure at the bottom, right? What you can do is you can use a key encapsulation mechanism. Key encapsulation mechanism is used to establish a symmetric key between communication partners based on an asymmetric key. So you use at the start an asymmetric key to encapsulate a symmetric key, send it to the partner, and then the partner basically encapsulates, decrypts this message and gets the a symmetric key. And we use that, or this is used in TLS, for example, because symmetric keys are much faster, or symmetric key algorithms are much faster in encryption, decryption than asymmetric keys. And we do this here in TLS based on both the classical RSA CAM as well as the new post-quantum ML CAM. Right? This is what we basically did. We also fiddled around with a Java library in this area and donated it to open source and so on. This is what we have basically done. And you can start today with this kind of code.
Absolutely. Actually, this is all, we were talking about this today, this is all open source. So if somebody wants to start now, not only, they don't have to invent anything. They just need to go to whatever has been approved, what has been even created for them by this consortium, which is the PQCA, right? And get started. And nothing is preventing you from starting now. Basically.
And this consortium, the Post-Quantum Crypto Alliance, this has members like Microsoft, Amazon, Google, IBM, and so on. So they work hard to roll out the implementation of the NIST standards, which, as Isabel said, is open source, and we used it in our own efforts in order to become quantum safe.
Now, this is a question actually asked Frank when we started all this, because working in security and knowing like the larger the key, normally the slower it is, the messages are larger, etc. So what is the impact that using quantum or using the combine, as we were just said, like if I'm doing this dual approach where I have both RSA and CAM at the same time, what is the impact? And actually we were pretty amazed by the results of the performance tests that have been done. So this is what you see here is like processing time depending on the type of algorithm which actually be used. The red ones are like pure RSA, right? The blue ones are RSA combined with CAM, right? And the last one is just CAM alone. As you can see, this is actually the faster, which is actually fascinating, Frank. You have any idea what was it so efficient in the end?
There's a lot of mathematics going on, and the mathematical algorithms have been improved over 3 decades. Okay, you can say the very same for RSA, but RSA was fast enough, right? Nobody was complaining, but in the meantime, the lattice-based algorithms are so extremely fast, but that they have been so fast was also astonishing to me. So once our colleagues in WSO2, the team made the measurements, I was deeply impressed how fast it really was, Isabel.
So there's really no worry to have like switching to that dual approach could have an impact, which is great. And also obviously, and there's another interesting picture here. So I'll let you explain this efficiency number. So for every algorithm, there is a measurement which is the efficiency of by bits. What is that about?
Okay, so you measure it by bits. Because if you have n bits, then the efficiency or the stability of the algorithm means you need 2 to the power of n operations in order to crack the key by brute force attack. That basically means the higher n is, the more secure a certain mechanism, a certain algorithm is, right? And here, Elizabeth, you see on the left side, on the right side, the blue algorithm is, so to speak, the efficiency of the new post-quantum algorithms. And then in the middle, on the right, you have the existing algorithms. And the existing algorithms, the efficiency, so to speak, for per step is very low. And the post-quantum algorithm are enormously efficiency, right? They can produce security in an unseen efficiency before. So we were also, again, absolutely fascinated about the algorithm. And at the very beginning, a couple of months ago, I didn't trust the results. When I've been with the team in Columbus and said, they made an inherent mistake. This can't be. Then they made it the second time, the third time. And then we asked again another effort. Now, recently, a couple of days ago, they run the tests again, and it didn't change. So we did see with a post-quantum safe TLS, we did see a little dependency on the environment. So surprisingly, on macOS, the algorithm was fastest, a little bit slower on Linux, and slow on Windows. Slow means it was fast, right? But so there isn't, but this is, if you measure the algorithm itself, it's unbelievably efficient here.
That's great news, actually.
Yeah, absolutely.
One of the things, like, again, when I started working with Frank on this, like a few months ago, that was in my world. Like, I didn't know much about quantum, but I don't mean like I do right now, but a little bit more than I do. And then what I didn't understand is, like, basically I was using this every day. Why am I using this every day? Because recently, and so any browser you may use, which is based on Chromium and Chrome, now has post-quantum cryptography as a default. So if it talks to a system, we were talking about TLS before, and the fact that we are actually having this dual approach on algorithms. So if the client is actually quantum cryptography aware, it will choose that over anything else. And actually, this is what happens, right? So if you actually connect to WSO2.com today, because of the platform we're using to hosting our website is actually ready for quantum cryptography. If you go to the developer tools, right, you look at how you connect, you will see that this connection is using TLS 1.3, great, but you also see this big name like 25519 MLChem, which is what we just discussed, right? The MLChem 768. So even if you don't know, you might be already, in that world and using that world already, because slowly and slowly, more and more, because of people being conscious that this is something we need to get, again, prepared for pretty quickly, it's already in the works and it's already established in many places. And one thing which is important, I think, is all the regulation around this, because there's obviously the first to realize that there would be problems here and want to protect themselves are the governments, right? So Frank, what can you tell us about those regulations and the potential?
So under Biden, on the left side, there was a quantum computing cybersecurity preparedness act that basically is a legislation that asks for each and every government organization in the US to roll out a plan within a couple of months. What it means to modify all their IT systems to become quantum safe. The plans have been developed. They are open. You can find them on the internet, and now they're already working to become quantum safe. A couple of months later, the EU on the right side did the very same. It's called the Coordinated Implementation Roadmap for the Transition on Post-Quantum Cryptography. So all the member states in the EU must come up with a plan, and so on, and so on, and so on. And in parallel, NIST, the National Institute of Standards, came up with guidelines how to transition to post-quantum cryptography standards. There is legislation, the little tiny thing, NIS2 in the lower left corner. It's a European law that basically asks the EU member states to categorize companies into critical and important. Critical are utility companies for water, power, and so on, and to provide everything that has to do with health and food and so on. And important are software companies and so on. And all these companies had to come up, so they were categorized until mid of this year. And now the people need to come up with a plan how to protect themselves against cyber attacks. And the law also contains threats to CXOs of the companies. That basically means the companies that don't prepare properly for these kinds of cybersecurity attacks, they need to pay up to 10% of their worldwide annual revenue as a fee to the EU government. And the companies may turn around to the CXOs to use their private money to contribute to the 10%. So the CEOs are now really under the gun that they can't say, I didn't know. They are under with their private money. And in addition, the law also says that such a CXO will never be allowed again to take a management position in any EU country. And similar is happening in the US, that is called CSF 2.0. So they also do the very same. In order to emphasize that, the NIST also did the classification of the existing and future standards. And what they basically say, that's in the upper right corner, that all the existing encryption standards like RSA, like elliptic curve cryptography, and so on, you can read it, are depreciated by 2030. And they are disallowed after 2035. That means in 10 years, it's already no. If you want to do any business in the US, right, and you use this kind of old-fashioned standards, it is disallowed. Right? This is why what Isabel said before. It is absolutely important that we all realize this threat and need to act now. Right, Isabel?
Absolutely. And actually, we're saying like it may seem far away, but it's not that far away. When you have to change the way you're working, etc. 2030 is like now almost. It's only 4 years from now. That's pretty close. Okay, so how are we going to help? Because this is WSO2. Up to now, we've not talked really about anything specific about WSO2. We've been kind of educating here. But obviously, we're doing all this research, and Frank is with us because we want to actually be quantum ready and help you be quantum ready. So what have we done so far? We have our own language programming language called Ballerina. People have been working with us. Maybe you're new to the WSO2 on this webinar, but we have our own programming language, which is post-quantum ready, right? So it means like you can implement what we described before. You can implement this dual approach to TLS as well, and you can also use those algorithms to sign and encrypt information through your Ballerina program.
But is even more. So if you build services based on Ballerina, right, and the communication between the remote services is protected because we have this TLS and so on. So you can build completely quantum safe applications in Ballerina. As I said before, we have an encryption library extended to use this quantum safe algorithm. If you want to store data, you can encrypt it with our library, store it in the database. So if you use Ballerina, Swan Lake, right, this is quantum ready.
Absolutely. And one thing we haven't talked really about right now is some specific verticals, right? But there are some mandates as well, in healthcare, in finance, on site. We've talked about government, right? But there are also some mandates, like if you talk healthcare, for example, it will be super important to make sure that all this data, which is manipulated, which is extremely sensitive, is properly protected, including in transit, right? In between services. So establishing that protection right now, as we said, at a very low cost, because indeed it's only like using a different library than RSA. We said it has no impact. Actually, even it could be even faster than what you're doing today to put data in between the systems. So they already know, anything like against doing this, like again now, right? And the same is true is obviously of our identity server, right? And using that to establish all the communications as well, with token endpoints, etc. Also through quantum. We're going to extend that to more products as well, right? From the work that we've been doing on identity server. Anything else on WSO2? What we're doing here in terms of?
I think that's fine for now.
Okay, wonderful. Well, that's what we had. So we're right on time. We wanted to finish actually at 30 minutes, even if we had a little bit more. So we just right on time here. Do we have any questions, Tasha? If you have any questions, please ask in the chat. We'll be more than happy to answer any of your doubts at this point.
I don't see any questions, Isabel.
I have no questions. All right. Well, that's fine. You can always reach us after. That's no problem.
Yes.
So there's one here.
Yes. No, I said yes, absolutely.
Yes, the Richard Dodge. Okay. So there was a question that popped up. All right. Well, thank you very much, Frank. We just touched the surface here because there's a lot behind in terms of technology. Obviously, if you have any questions, like Frank is your man. If you have any questions on quantum computing, we'd be more than happy to help. And please contact us again if you need any more information on our products and how to use quantum in our products.
With this one final question, whether the recording will be available for training and education. This, I think.
Absolutely, right? Like we do for all our webinars, we're going to you're gonna get the recording as well as the slides, which are freely available. This should happen in a couple days, maybe mid of next week. You will have that.
Okay.
Okay. Thank you very much.